Hello, students. This is an educational video created by Scholars Academy for CBSE Class 8 students. I'm so thrilled to have you here today because we're going to unlock some of the absolute coolest secrets in math. We are talking about the magic of squares, cubes, and their trusty sidekicks, square roots and cube roots. By the time we're done here, you're not just going to see numbers as boring digits on a page. Nope. You'll see them as these beautiful, predictable patterns and actual 3D shapes. All right, let's dive right in. Here's our roadmap for today's masterclass. First up, the royal locker puzzle. Then we'll hit squares and square roots, followed by cubes and cube roots. After that, we'll look at some mind-bending math patterns, take a quick stop in math history with the Babylonians, and finally, we'll wrap up by solving the exercises together. Let's do this. Section 1, the royal locker puzzle. Go ahead and put your detective hats on because we've got a mystery to solve right out of the gate. Imagine this. Queen Ratnamandri leaves her massive fortune to her son, locked in a secret room with 100 lockers. Now she brings in 100 relatives. Person 1 opens every single locker. Person 2 toggles every second locker. So if it's open, they close it. If it's closed, they open it. Person 3 toggles every third locker, and so on, all the way to person 100. The son figures out that the secret passcode is the numbers of the first 5 lockers that were toggled exactly twice. So what does this actually mean? It's a perfect real-world example of mathematical factors. A locker is only touched by people whose numbers are factors of that locker's number. So ask yourself, which numbers have exactly 2 factors, just 1 and themselves? Prime numbers. That means our winning passcode lockers are 2, 3, 5, 7, and 11. Pretty brilliant, right? Section 2, squares and square roots. That puzzle is actually the perfect setup for what happens when a number partners up with itself. Let's talk about perfect squares. So for any number n, when we multiply it by itself, we write it as n squared, or n with a little 2. But hey, don't just memorize this as some abstract rule. Picture an actual physical square. If I tell you a square's area is 49 square centimeters, how long is one side? Well, area is side times side, and what number multiplied by itself gives you 49? Yep, 7. So the side is 7 centimeters. This perfectly shows what a square root is. The square root, which is that little radical symbol you've probably seen, is basically just asking, hey, what number did I multiply by itself to get this area? So 7 is the square root of 49. And look, this rule isn't just for whole numbers. If you have a fraction, say 3 over 5, you just square the top and the bottom, boom, 9 over 25. A decimal, like 2.5, multiply by itself, and you get 6.25. Now here's a really cool twist. What's the square root of 64? You probably just shouted 8, right? Because 8 times 8 is 64. But what about negative 8 times negative 8? 2 negatives make a positive, so that's also 64. Every perfect square actually has 2 integer square roots, a positive and a negative. But just to keep things super straightforward for this chapter, we're mostly going to stick to the positive ones. Section 3. Cubes and cube roots. We've mastered the flat, 2D world of squares, so let's level up and step into the 3D universe. Welcome to the world of cubes. A perfect cube is when you multiply a number by itself and then by itself one more time. So 3 times total. N times n equals n cubed. Geometrically, try to picture those little 1 centimeter wooden blocks you probably played with as a kid. If you want to build a larger, solid cube with a side length of 2, you need 2 blocks for length, 2 for width, and 2 for height. 2 times 2 times 2 is 8 little blocks total. What about a side length of 3? 3 times 3 times 3 gives you 27 blocks. Numbers like 1, 8, and 27 are our perfect cubes. And just like squares have square roots, cubes have cube roots, which we show by putting a tiny little 3 right outside that radical symbol. But what happens when you're staring at a massive number, like 3,375, and you have to find its cube root? Enter our ultimate superpower, prime factorization. Think of this like holding trials for a sports team. To make it out of the cube root house, you have to form a team of exactly 3 identical numbers. When we factor 3,375, we get 3 times 3 times 3 and 5 times 5 times 5. Look at that, a perfect team of 3 3s and a perfect team of 3 5s. Each team gets to send 1 player outside the root, so we pull out a 3 and a 5. Multiply them together, 3 times 5, and boom, our cube root is 15. Easy, right? Section 4, mind-bending math patterns. Because math isn't just a bunch of boring rules to memorize, It is actually full of beautiful, predictable patterns. Let's look at this missing numbers puzzle from your textbook. The first row is 1 squared plus 2 squared plus 2 squared equals 3 squared. Next row, 2 squared plus 3 squared plus 6 squared equals 7 squared. Okay, can you spot the horizontal pattern here? Look at the first two base numbers. In the third row, 3 and 4. If you multiply them together, 3 times 4, you get 12, which is the third number. And look at the answer on the right, 13, which is exactly 1 more than 12. Okay, let's test this aha moment on the next row. 4 squared plus 5 squared plus, well, 4 times 5 is 20, so 20 squared. And the answer has to be 1 more than 20, so 21 squared. Let's jump to the absolute last one. 9 squared plus 10 squared. 9 times 10 is 90, so the blank is 90 squared. Add 1, and our answer is 91 squared. See? Once you spot the pattern, you don't even have to do the heavy calculating. Section 5, Math History, the Babylonians. Let's take a super quick breather and hop into our time machine. You know, the very tools you're mastering right now were actually pioneered by the ancient Babylonians, way back around 1700 BCE. They literally carved lists of perfect squares and perfect cubes into clay tablets. Why? Because they were building these massive ziggurats, measuring out huge plots of land, and designing complex architecture. They needed fast ways to calculate area and volume, just like modern architects and engineers do today. So you are quite literally learning the foundational math that helped to build human civilization. How cool is that? Section 6, Solving the Exercises. All right, scholars, it is time for the main event. It's one thing to watch me explain all this, but it's totally different when you have to do it yourself. So let's tackle these textbook exercises together. I know staring down a list of math problems can feel a bit intimidating, but I want you to take a deep breath. We've got all the tools we need in our mathematical toolbox. We've got our factor pairs, our teams of 3, our pattern recognition. You've totally got this. Let's go. Question 1 asks us to find the cube roots of 27,000 and 10,648. Let's think this through logically. 27,000 looks huge, but really it's just 27 times 1,000. We know 27 is 3 cubed, and 1,000 is 10 cubed. Combine them and we get 30 cubed. So the cube root is just 30. Super simple. For 10,648, let's use our prime factorization. If we divide it all the way down, we'll find 3 2s and 3 11s. Hey, that's a team of 2 and a team of 11. 2 times 11 is 22. So the cube root is 22. See? Always break big, scary problems down into small, easy steps. Moving to question 2, what number will you multiply by 1,323 to make it a perfect cube? Remember our teams of 3 rule. Let's factorize 1,323. Dividing it out, we get 3 times 3 times 3 and 7 times 7. Uh-oh, look at the 7s. There are only 2 of them. They are missing a partner to make a full team of 3. So what do we need to multiply the whole thing by to fix it? You guessed it, we just need 1 more 7. Multiply by 7 and bam, it becomes a perfect cube. Now for question 3, the true or false round. Statement 1, the cube of any odd number is even. Let's test that. What's the cube of 3? 3 times 3 times 3 is 27. 27 is definitely odd, so this statement is absolutely false. An odd number times an odd number is always odd. Statement 2, there is no perfect cube that ends with 8. Think back to our unit cubes. What is 2 cubed? 2 times 2 times 2 is 8. So right off the bat, we know this is false. And if you want another example, 12 cubed is 1,728, which also ends in an 8. Let's keep going with true or false. Statement 3. The cube of a 2-digit number may be a 3-digit number. Let's take the very smallest 2-digit number, which is 10. 10 cubed is 1,000. That already has 4 digits. Since that's the absolute minimum, it's literally impossible to have a 3-digit cube from a 2-digit number. False. Statement 4 says a 2-digit cube may have 7 or more digits. Okay, the largest 2-digit number is 99. Well, 100 cubed is 1,000,000, which is exactly 7 digits. Since 99 is smaller than 100, its cube has to be less than a million, meaning it can only have up to 6 digits. False again. Finally, statement 5. Cube numbers have an odd number of factors. Let's test the perfect cube 8. Its factors are 1, 2, 4, and 8. That's 4 factors, which is an even number. Actually, only perfect squares have an odd number of factors. So this one is false too. Question 4 asks us to guess cube roots without factorization. Wait, how is that even possible? I'm going to teach you a super brilliant shortcut using unit digits. Look at 1331. It ends in a 1. The only single digit that cubes to end in a 1 is 1. And since 1331 is bigger than 10 cubed, which is 1,000, the root just has to be 11. Now look at 4913. It ends in a 3. What single-digit number when cubed ends in a 3? Well, 7 cubed is 343, so our root must end in a 7. And since 4913 is between 10 cubed and 20 cubed, the answer has to be 17. Let's do 12,167. It ends in 7. Since 3 cubed is 27, our root ends in 3, making it 23. Finally, 32,768 ends in 8. 2 cubed is 8, so the root ends in 2. Since 32,000 is between 20 cubed and 40 cubed, well, it's 32. This pattern is literally a mathematical superpower once you get the hang of it. Okay, finally, question 5. Which of these successive differences is the greatest? 67 cubed minus 66 cubed, 43 cubed minus 42 cubed, or the squared versions of those numbers? Remember the leveling up concept we talked about earlier? Squares are 2D area. Cubes are 3D volume. Volume grows exponentially faster than area. So right away, we know the cubic differences are going to be way larger than the square differences. And between 67 and 43, 67 is the much larger base number. So subtracting a massive cube from an even more massive cube is going to yield the biggest gap. That means 67 cubed minus 66 cubed is the greatest. No heavy calculator math required, just pure logic. We have covered some seriously incredible ground today. Let's recap the crucial takeaways. Squares and cubes are all about multiplying a number by itself, and their roots are simply the inverse operation. You're just working backwards to find the base. When you get stuck on a huge number, grouping prime factors into pairs or teams of 3 is your ultimate fail-proof tool. And most importantly, remember that math is absolutely full of shortcuts and patterns, just waiting for you to notice them. You guys did fantastic work today. Math is a total adventure, and you are building the exact same logical skills that those great ancient architects used to build empires. I'll leave you with one final kind of mind-bending thought. We mastered the 2D square today, and we easily calculated the 3D cube. But what do you think the math looks like for a 4-dimensional hypercube? Keep exploring, scholars, and I will see you in the next one.